graphs. Okay, so I'm going to start recording now. And so again, these practice problems and these lectures will be on Canvas for you guys. And so let's get into it. So let's take a look at this problem. So in this problem, we're reacting zinc and a sulfuric acid. So in this situation, you guys know how we just had the tube connected to the flask, right? The reaction is happening inside of the flask. So in this flask, we have solid zinc, and then we're adding sulfuric acid into it, okay? Now, if 159 milliliters of wet H2 is collected over 23 degrees and the barometric pressure is 738 torr, how many grams of zinc has been produced? Now, there's a lot of things going on there, so let's just break it down real quick. So the 159 milliliters is basically telling us, hey, if you look at this reaction, if we mix sulfuric acid and zinc, it's going to create, the only gas we're going to make is H2 gas, right? So if it tells us that 159 milliliters of H2 was collected over water, it just means that the H2 gas, because the gas is the thing that ends up coming into this container, it means that the volume of the gas produced was 159 milliliters, okay? So if you guys want to draw this somewhere on your paper, I recommend it because, again, it's a good way to visualize what's going on in this problem. But basically, again, it's telling us H2 gas is the gas that's produced. So if we trap it underneath the water or on top of the water, it's just telling us that it takes up 159 milliliters of space. Okay. All right. It's also telling us that the temperature is 23 degrees Celsius. So you can kind of start to see what kind of variables we're getting, right? The volume of the gas, of H2 gas, is 159 milliliters. I'm just going to convert that actually to liters. We can just do 0.159 liters. The temperature is 23 degrees Celsius. And then it tells us the pressure is 738 torr. Okay, so the pressure of H2 gas is 738 torr. And what we're looking for is how many grams of zinc has been consumed. Okay, so we're looking for grams of zinc. But if you guys look at the back of the problem, it tells us the vapor pressure of water is at 23 degrees is 21.07 torr. Okay, so that might seem a little bit strange, okay, because we just collected H2 gas, right? So H2 gas is the thing that is inside of this container, trapped on top of the water, okay? But there's a property about water that we need to know. When you have like a cup of water, or if you just have a container of water, the water molecules don't all stay liquid. It's kind of weird, but you guys kind of know how they evaporate, right? Water evaporates off the top. Now, even if you're not heating up the water, even if it's not boiling, some of the water molecules on the top of the water is just going to turn into gas. It's really strange, but it doesn't all just stay liquid. It's a very small amount, but some of the water molecules are going to come out of the liquid water and they're going to be gaseous H2O molecules. Does that make sense? Now, we learned last time about partial pressures, right? So what that means is on top of the graduate cylinder, remember how when we trapped the gas, it wasn't just H2 gas, like I said right there. Okay, there's also another gas in there. The other gas in there is some of that H2O. Some of the water molecules on the top level of the water is vaporizing into H2O gas. And so there's two different gases in there. Okay, and so what that means is we need to use, and that's what the vapor pressure of water is. That's the pressure that is created by the H2O gas molecules. And so there's two different pressures in there. There's the pressure of H2 gas, and there's also the pressure of the H2O gas. Does that make sense? Okay, so basically on the top, it's a mixture of gases. It's the gas that we make using the reaction right here. And there's also the gas caused by the natural vaporization of the H2O molecules. What's up?
Well, the pressure caused by the water
it depends on the temperature, which makes sense, right? Because if you're boiling it, like a lot of it is going to move out. And so there's usually like a table. If you guys go to the back of the textbook, there's an appendix that has it at different temperatures. But most of the time, you'll be given the vapor pressure at this temperature. That's why it specifies at 23 degrees Celsius. Great question. Yeah. Sorry, can you repeat that real quick? How much the volume of the gases that's captured above the water? Yeah, so it's like what we did in the demo. It was at a certain level, right? And there's like a marking. So here it's like 100. And then if we run the reaction and it goes down to like 50, that means the amount of gas that was produced is 50 milliliters.
Yeah, but I'm sure that there's some gases that are very
Oh, is it reacting with water? That's very minuscule. Water does not really react as a gas. It's pretty inert. And so even if there are some reactions, it's not going to change your calculation any significantly. That's a great question. Yeah, it's not going to react with water, especially H2 gas. That thing does not react with water. We'll talk about how to kind of determine that and predict that in future units. But yeah, don't worry about it reacting with it at all. Great question. Dang, you guys are really thinking outside the box now. You guys are really testing me. See if I know what I'm talking about. It's tough because I'm making this up as I go. Okay, so we have two different pressures. Okay, and so in order to figure out how many grams of H2 are produced, what we have to do is we need to find the pressure of H2. Oh, sorry. I actually made a mistake right here. The barometric pressure is not the pressure of H2, it's the pressure, total pressure. I'm sorry about that, guys. Yeah, barometer is like if we have a measurement tool in here that tells us the pressure, that tells us the total pressure. My bad. It doesn't separate out the pressure of the individual gas. Sorry about that, guys. Just to clarify again, I said this was pressure of H2, but barometric pressure, if you ever see this, this is always talking about the total pressure. I'm so sorry about that, guys. It's a Friday. I haven't taken my morning dump, so brain's a little slow. Okay. All right, and that's why we need to know the pressure of the H2O because, again, the partial pressure, right? The total pressure is made up by the constituent pressures. If we want to find the pressure of H2, we need to use the total pressure and the pressure of H2O. That'll let us find the pressure of H2. And then after that, we can use PV equals nRT to find the grams of zinc. Okay, so I know that I kind of gave you the steps laid out. I didn't explain it fully so you guys can try figuring out the end, but I'll give you guys maybe about a minute and a half. Try solving out this problem. We have all the variables up there. And using that, I want you to find the grams of zinc that's produced. You're going to have to use partial pressure. You're going to have to use the ideal gas law. And then you're going to have to use stoichiometry to find the grams of zinc. So a lot of different steps. This is an FRQ question that shows up sometimes. So try it out. You can work with the person next to you. But if you don't get it, just try your best. We'll go over it in just a second together. Not thank you. Because you guys work so hard, everything's caught up. My car needs to walk if you want to park out. I have an honest question to ask all of you. You guys go take a bath today at home. Are you gonna fart underwater about this? I am right now. Because I definitely will. You guys will? Good, good. every time you fart in the water now, I want you to think about this lab and this problem, this demo of this problem. I know, lifelong question. So the gas that comes out of your butthole, you can actually collect it into a container and measure how much gas came out. And then you can subtract the vapor pressure of water at the temperature you're at, and you can calculate how many grams of fart molecules you actually face. That should be a competition. It should be. Who can produce the most? Bruh. The easiest thing to do is just eat a lot of beans, unwashed beans.
It's the refried. Like if you have like meat from the pot or whatever, you
Yeah.
don't do it.
You know why? It's because if you put beans in water, it takes the gases out. So I don't know if you've ever done it, but if you buy beans and you put it in water for a bit, all these gases come out. And so that's why if you eat a lot of beans that aren't washed, you fart a lot, because all those gases that come out, that starts coming out of your butthole. That's why you fart a lot. Fun fact from this girl, guys.
Nice. Is it still recording?
Yeah, it is recording.
Okay.
Please don't show this to your parents. They're gonna think I'm a weirdo. Probably already do though. Anyway, I'll give you guys 30 more seconds to try finishing that up. I don't know. Think you got it? I hope so. I actually love it when you guys get questions right because it's easier to grade. I don't really care so much about what you get on the test, but it makes it a lot easier for me to grade the test. Selfish like that. Nah, but then I don't know if y'all are actually learning, and I'm pretty sure.
We're learning.
Sure. Sure you are.
We're trying our best.
Alrighty, guys. So if you guys are finishing up, same as usual, you can kind of zone me out while you guys finish, and then just make sure you check your answer at the end. But if you are done, let's check your answers. And if you didn't get it, it's all good. We can figure it out together. Alrighty, guys. So let us start by doing some calculations with the partial pressure. So we said that the total pressure is 738. And so if we write the total pressure is equal to the pressure of H2 gas that was produced and the pressure of the H2O gas that was created by the vapor pressure. All we need to do is rearrange this equation, and the pressure of H2 gas is equal to the total pressure minus the pressure of H2O. So hopefully that part wasn't too bad, just basic manipulation. So all we need to do is 738 torr minus 21.07 torr, and that'll give you the partial pressure of H2, which is 716.93 torr. Okay. All right. Now, the way I do it is I kind of like putting everything in terms of atmospheres, just because the numbers are a little easier to work with. So if you guys didn't do this next part, that's totally fine. If you use a different R value, that's fine. But I'm just going to convert this into atmospheres. It's 760 torr per 1 atmosphere. So if you want to, you can convert this into atmospheres by dividing by 760. And that should give you 0.94. Okay, and again, if you kept it in torr and you use this R value that applies to torr, that's fine. We're going to get the same answer. But I just personally like using atmospheres just because I like small numbers. Okay, I'm a small person, so I like small numbers. Okay, so the pressure of H2 is equal to 0.943 atmospheres. Okay. All right. So that's how we get the partial pressure of H2. Now let's use the ideal gas law. Now, in this problem, we're gonna look for grams of zinc. This is what we're looking for. And so if we have PV equals nRT for H2, which of these values do we need to find? PV, N, or T? If we're trying to find grams of something, which one of these do we need? Yeah, N, right? Because N is moles. And so what we can do is we can rearrange this equation to N equals PV divided by RT. Again, if you solved it out and just kind of made sure the numbers were correct, that's fine. You'll get the same answer. I just like rearranging it so I can just plug and chug in one go and just finish it up. All right, and again, we're looking for moles. This is N of H2. So I'm just going to specify that. If you didn't, that's fine. All right, so if we're solving for N of H2, the moles of H2, let's plug in the pressure of H2, which is 0.943 atm. The volume of H2, this is the amount you collected over the water, which is 0.159 liters. Oh, my voice cracked. And then you have 0.0821, and that's your value of R. If you guys did the value of R for torr, that's fine too. I think it's like 8 point something or whatever. And then for the temperature, you have 23 degrees Celsius. You just need to make sure you add that to 273.15 in order to turn that into Kelvin. So that's 296. Yeah, 296.15 Kelvin. Okay. All right. And again, if you guys set it up a little different, your numbers might look different, especially if you use torr. I turned it into ATM, but if you kept it torr, you'll get the same answer as me at the end. So let's plug and chug and see if we got the same thing. We got 0.943 times 0.159, and that's going to give you on the top 0.1499. We're going to divide that by 0.0821, which is the R value, and then we're going to divide that by 296.15, and that's going to give you 0.00617. Okay, so 0.00617 moles of H2. Okay, so I'm going to stop right there just to make sure we're all on the same page. Any questions about that? Y'all chilling? Yeah, what's up, Craig? Yeah, so we said earlier that when you mix these two things, zinc and sulfuric acid, it's going to make that gas, right? And then it's going to trap it on top of the water. So the gas that's made in this reaction is H2. So through the tube, H2 is going to it's going to travel, and then it's going to get trapped up there. But some of the water on top of the water is going to vaporize. And so inside, on top of the collected area, there's going to be H2 and H2O. And so we just used the given value of the partial pressure of H2O, and then we just subtracted that from the barometric pressure, which is the total pressure, and that gives you the pressure of H2. It's just the partial pressure equation, where total pressure is the pressure of H2 plus pressure of H2O. Okay. Does that make sense, or still a little confusing? You got a different value? Yeah, so that's in torr. I converted that into ATM. So I forgot what did you get, 716?
Yes.
Yeah, so 716 torr. I like to convert it into ATM by using the conversion, but if you kept it 716 torr, that's fine. It's just that this value down here, the R value, is going to be different than the one I used. It's going to be the one that has torr inside. As long as you get the same number of moles, you're good to go. Okay. Yeah. Only if you have to. Again, usually you'll be given the R value for both, but I'm actually going to give out the equation sheet that they give you on the AP test. And so you guys can check out if you guys need to convert it. But usually they give you the one for torr and atmosphere. Okay, good question. Any other questions? Okay, so this is the value that we got for the moles of H2. Now, if we take a look at the equation, we're looking for the amount of zinc that was used. We have a balanced equation. So what we can do is just use this to find out the moles of zinc. Now, this is balanced already. So it's a 1-to-1 ratio. So we're actually going to end up with the same number of moles of zinc. Does that make sense? Since it's 1 mole of H2 per 1 mole of zinc, we can just say that it's the same number of moles. It's going to be times 1 divided by 1. Okay. I'm going to erase this. And then from here, we just need to do one final conversion, and then we'll be all done. All we need to do is take the moles of zinc, which is 0.00617 moles of zinc. If I want to turn moles into grams, where do I get the numbers from?
Periodic.
Yeah, the periodic table. Okay, so it's going to be 1 mole of zinc, and yeah, 65.39. Okay, grams of zinc. So this is all going to come from the molar mass. And so we are almost done. All we need to do is multiply by 65.39. And that's going to give us a final answer of 0.403. Okay, so in this reaction, 0.403 grams of zinc were consumed in the reaction, and that's how it made the H2. Okay, so if you guys got that, great work. If not, that's fine. I know there's a bunch of different things, but this is why I said you really need to make sure you guys do the work with the practice problems, because a lot of the problems on the AP test, they're not fair. You're not going to be able to see every type of problem just because they mix and match these different methods of doing things. And so that's why it's important to put in the work on the basic stuff. That way you're able to do these more challenging combined problems.
On the effort to how would it like be formatted? Like, but this could be like when the end, right?
Yeah.
So then like what would be like 8.
So usually this type of problem is not going to be on the MCQ, because MCQ you don't have to do a lot of calculations like this, but they might ask you conceptual things like the total pressure, and you would have to know, hey, I need to subtract the pressure of H2O. Okay, any questions about this one before we move on? Alrighty, let us move on. So let's take a look at the next section. So another thing they'll ask you about gases is something called a mole fraction. Now, mole fraction is basically the moles of a compound divided by the total moles. It's basically like a percentage or like a ratio. It's just used in a different term. Okay, it's the ratio of the number of moles of one component in a mixture. So this is if we have a container with different types of gases in it. Okay, the mole fraction is basically the moles of one component divided by the total moles. Okay, but since each gas in a mixture, they're kind of independent from one another, we can determine the mole fraction based on the pressure. So based on the partial pressure of each one, we can figure out what the moles are as well. Okay, so we're gonna take a look at the next problem. And so let's take a look at this one. So it's telling us to calculate the partial pressure of O2, okay? So in a container, it's basically telling us, if we look at it, there's 1.5 moles of CO2. I'll do that one in blue. CO2 is blue. So we got 1.5% of the mixture is CO2. 18% is O2, okay? I got some more. But then most of it is made of argon. So I'll do black for argon. Okay, so there's mostly argon in here. There's some CO2 and there's some O2. Okay, so there's a big mixture. And these are the percentages. It's asking us to calculate the partial pressure of oxygen if the total pressure is 1,000 torr. Okay, so what the mole fraction is basically telling us is that depending on what the percentage is based on moles, you can also find the pressure. So if you notice, oxygen is 18%, right? So if I want to find the pressure of just the oxygen, all I need to do is take the total pressure, which is 1,000 torr, and just multiply it by 18%, which is 0.18. Okay. So if you get that, you should get 180 torr. That's basically what this concept is telling you. Okay. So if you know the percentage of a mixture that is made out of one gas, you can figure out what the pressure is. The pressure has an equal relationship with the number of moles. Okay. So that one's kind of a gimme. It's pretty simple. All you need to know is that the pressure and the moles have a one-to-one relationship with one another. Okay. All right, any questions about that? And I think we'll finish this unit today. And that way, the next two class sessions, we're just gonna do a bunch of practice problems so you guys can prep for the exam. The next exam is gonna have stuff from the previous exam, the previous unit, solutions. And so we'll do practice problems for this unit and for the previous unit. All righty. Now, this next concept is basically what this entire unit is built on. It's kind of weird that we're doing it at the end. It's called the kinetic molecular theory. Now, you guys already know the kinetic molecular theory. You guys just haven't put it into words yet. But basically, the way that you understand gas molecules is the kinetic molecular theory. Okay, so I'm just going to read through them. You don't need to write it down. You don't need to memorize this unless you don't know one of these. It's just conceptual stuff that will you use to figure out different theoretical problems, okay? Again, you guys know this stuff already. So gases are made out of a lot of particles. They're individual molecules, okay? And they're constantly moving, and they're moving around. They're flying around everywhere, okay? We all know that, right? Okay? The volume of the particles is negligible to the volume of the container, which means that the actual space that the actual molecules take up is a lot less than the space of the container. So if you have a balloon, right, most of the balloon is empty space. There are some gas molecules, but there's not a lot. Since they're flying around, that's what allows the balloon to keep the shape. That's what it's telling you. Okay, attractive and repulsive forces between the particles are negligible. Basically, they're not really interacting with each other. They're not bouncing off each other. They're not chemically reacting with each other. They're just kind of there together. Okay, energy can be transferred through collisions, but the average kinetic energy does not change as long as the temperature is constant. Okay, so as they're flying around, they can bump into each other and they'll transfer energy, but the only thing that'll really change the energy in there is gonna be the temperature. Okay, so just know temperature affects how much force these guys have. It affects the pressure and the temperature. And then Kelvin temperature is proportional. So we use Kelvin. That's basically what it's saying. So all of this stuff should be pretty much things you guys already know. We've been talking about this for a while now. We just kind of put it in writing. That way we know what's going on. All right. So this little graph right here is called the Maxwell-Boltzmann distribution. And basically all it's telling you is the kinetic energy. Kinetic energy is how much energy something that's moving has. It becomes greater as the temperature increases. So I'm going to zoom in a little bit. So if you guys take a look at this, the black line is at 270 degrees Kelvin. The red line is at 373 Kelvin. And the blue line is 473 Kelvin. So basically, those are the temperatures. Okay, and then on the x-axis, we have the speed, how fast the molecules are moving. And then the relative frequency is basically telling us what percentage of the molecules are moving at that speed. So if we take a look at it, at 200 for this red one, about 4% of the molecules are moving at 200 meters per second. That's basically what it's telling. And then here at 400, about 11% of the molecules are moving at 400 meters per second. Okay, that's how you read the graph. So if you guys take a look at this graph, remember the black one is 273, the red one is 373, and the blue one is 473. And so if you guys take a look at this graph, you guys should notice as we increase the temperature, what happens to the percentage of gas molecules that get faster? Yeah, we have more gas molecules moving faster, right? So here, look at the peaks. most of the gas molecules at 273 are moving just under 400. But then here, most of the gas molecules are moving above 500 and then closer to 600 as we go up in temperature. And a higher percentage of them are moving faster. That's basically what this graph is telling us. It's just a fancy way of telling us, hey, you increase the temperature, they start moving faster and they have more kinetic energy. Okay? Now this is the kinetic energy equation. You guys might want to jot this down somewhere. Kinetic energy is equal to 1/2 mass times volume squared. Okay? So the amount of kinetic energy something has is equal to the mass, right? How big something is, because it hurts more if you get hit by a truck than a bicycle, right? And then the speed it's moving at, right? It hurts more to get hit by a car moving at 40 miles per hour versus one that's moving at 10 miles an hour, right? So, oh, interesting. You couldn't dodge it? I'm sorry. I'm sorry. Yeah, I got hit by a car when I was a kid too. Yeah. Anyway, yeah, so kinetic energy, the amount of energy something moving has depends on the mass and the volume. That's basically what you need to know, okay? All right, let's go on to, oh, and then, yeah, let's try out this problem. Okay, so you guys might want to use your Chromebooks to do this one just because so you can see the graph a little bit better. If not, that's okay. Just kind of eyeball it. But we're going to be estimating the fraction of molecules at 0 degrees Celsius, okay, 0 degrees Celsius, that has a speed less than 400 meters per second, okay? So we're going to be taking a look at this graph. 1, 2, 3, 4. This is 400 meters per second. I want you guys to just kind of eyeball, estimate, right? What percentage of the molecules at 0 degrees, 0 is this blue one right here, what percentage of them are moving at less than 400 meters per second? So it's the blue one. So what we want to do is we just want to look at the area under the curve. So I'm gonna just color it in. So if we just look at the percentage, what percentage-ish of the molecules at 0 degrees Celsius are moving at less than 400 meters per second? Like 40-ish, like, yeah, about half, right? Because if you take a look at the other side of the curve, I'm gonna draw it in red. I guess it's a little bit more than half on the other side, right? So about, I'll just say about like less than 50%. We'll say 40%. Okay, so 40 to 50%. Okay, and so it's asking for an estimate, so you don't have to be super specific. But if you take a look at it, about 40 to 50% of the molecules are moving at less than 400 meters per second. Okay, so just get comfortable looking at graphs like this because the AP test will give you graphs that have multiple lines on it, and you have to be able to distinguish between the lines and look at them independently from one another. So that's kind of the point of this problem, because there's one that's at 0 degrees and one that's at 100 degrees. Okay, and then if you look at 100 degrees, the fraction of molecules moving at less than 400 is a lot less than the ones at 0. Okay, just make sure you guys keep that in mind. Alrighty. Okay, so we're gonna move on, talk about kinetic energy again. Okay, we already have the formula. Kinetic energy is calculated by 1/2 mv squared. And so basically, this formula tells us that if you have less mass, you need more velocity to generate the same kinetic energy, which makes sense, right? If a bike wants to have the same kinetic energy as a car, the bike's you got to be pedaling real quick to have the same kinetic energy. A car doesn't need to move as quickly just because the mass is bigger. And the same thing is true for gases, right? Because we know about molar mass, right? Some molecules are bigger than others. And so the smaller molecules, so for example, H2, it needs to be moving a lot faster, right? This is the speed. They need to be moving a lot faster than, let's say, O2 which is 32 grams per mole, and H2 is 2 grams per mole. H2 needs to move a lot faster to have the same energy as O2. Okay, that's pretty much what this graph is telling us. So if you guys take a look at it, it kind of tells you various gases, and it makes sense. O2 is 32 grams per mole, N2 is 28 grams per mole, H2O is 18 grams, helium is 4, and H2 is 2. So the bigger the gas molecule, the less speed it needs to have the same kinetic energy. That's pretty much what this is telling us.
Okay. Throw a bullet.
Yeah, if you throw a bullet, it's not going to hurt, but if I throw a brick at you, it's going to hurt, right? So same concept. Okay. All righty. All right, I think this is one of the last concepts that we go over. Maybe there's one more. Oh, this is the second last concept. So we're almost done. Okay, so gases, we talked about how they spread out, right? And again, I'll give you that very graphic image of a fart. You fart on one side of the room, it spreads to the other side, okay? And so that effect is called diffusion. Diffusion is once a gas, it mixes with one substance with another. So if you look right here, this first one is the same thing. If I have a wall blocking my fart, right? So like, let's just say that there's a partition right here. It's gonna block my fart from going from one side of the room to the other. But if I open that partition, right, the fart is gonna travel through from one side to the other, okay? So that's an example of diffusion. Okay, effusion is actually how farts work. It's where a gas escapes from a container through a small opening. Okay, so I don't need to describe that too much, right? So you guys know how you guys do effusion on a daily basis. Okay, I'll just leave it there. Sorry. You want me to elaborate on effusion? You're weird, dude. Y'all know how effusion works. Some of you guys might be holding back effusion right now. All right, so that's diffusion and effusion, okay? So why is this important? So we just talked about how some gases are smaller than others, right? And so, oh no, you guys can't see that yet. Okay, so what that means is, we said earlier, smaller gases have to move faster to have the same kinetic energy, right? Kinetic energy is directly relational to temperature. Okay, so if we're at the same temperature, smaller gases need to move faster than heavier gases. So they have higher rates of diffusion and effusion, okay? So the bigger the gas, the slower it moves, so the slower it spreads out across the room, okay? Whereas the smaller the gas, the faster they move and the faster they spread out across a room. That's basically what this formula is telling you. Okay, and you guys don't need to memorize this formula. Just know that R, this has to do with the rate of the gases. And then this, remember mu, this has to do with the molar mass. Okay, so basically this formula tells us the bigger the gas, the slower it's gonna spread out. The smaller the gas, the faster it's gonna spread out. Okay. That's why I think, actually, never mind. I thought about it, it's not true. I was gonna say that's why I think silent killers, they move a little bit more slowly because there's more heavy gases in there that make it smell really bad. But you know, silent killers, you guys know what silent killers are, right?
I thought you were talking about like a murder.
No, I'm talking about farts, silent killers, the ones that are quiet but smell really bad. They kind of creep up on you, you know? Like somebody farts and you don't know for a while, but then eventually you smell it. But I think it's because there's like heavier compound. This is Mr. O's Wikipedia, like not very well researched thoughts, but like it smells bad because there's bigger particles, right? And so it moves slower. Whereas like ones that don't smell too bad, it just kind of spreads out or smells less bad. Anyway, moving on. Okay, last thing for today. I don't even know what I'm talking about at this point. All right, let's move on. The last thing we're going to talk about is gas stoichiometry, because like I said, you will never, ever, ever escape stoichiometry in this course or in chemistry. So we have two problems. I know. Dude, you guys signed up for this class. I told y'all it's gonna be a lot of math.
What if
So,
we drop out that hurt, right?
dude, drop out. Bye. Have a good life. No, I'm just playing. I love all of you. If you guys leave, I'll cry. All right, so we're gonna be doing two gas stoichiometry problems. And so again, if at any point you feel confident doing this on your own, go ahead and do so. You guys have all the tools that you need: ideal gas law, molar mass. You have stoichiometry, so you guys can figure this out. But I'm gonna go through the first one step by step. After that, I'm gonna let you guys try the harder one, the next problem, on your own. And then after that, we'll be all done for this unit. So I think we will finish today. Okay, so let us start. So in this problem, it tells us if you allow 15 grams of NaClO2, so we have 15 grams of this guy, it's gonna react with 2 liters of chlorine gas. Okay, the pressure, oh, I'm gonna write it up there. The pressure is equal to 1.5 atm, and the temperature is 21 degrees Celsius. It's asking us how many grams of this guy right here, ClO2, can be prepared. Okay, and the hint tells us you need to look for the limiting reagent. Okay, so what we want to do first is we want to figure out what the limiting reagent is. That way we can figure out how many grams of ClO2 can be prepared. So let's start with this guy right here, NaClO2, because this is just regular stoichiometry, okay? If I have 15 grams of NaClO2, do you guys think you could find the grams of ClO2 that's formed?
Yeah.
Hopefully. So try that out. This is just normal stoichiometry. I want you to take this value and find the grams of ClO2 that can be prepared. Okay, so I'll give you guys a minute. This is just normal stoichiometry. All right, maybe 30 more seconds to finish up that stoic problem. If you guys are done, just kind of hang out for now. If you want, you guys can try finding the Cl2 one. You'll need the ideal gas law. You guys can try that out too. But we'll go over the stoic, and I'll go over the ideal gas law one step by step. Alrighty, guys. So I'm gonna go over the stoic real quick. So if you guys are working on the other one, again, you can just check your answer at the end. But if you didn't get it, just make sure you're following along. Okay, so what we want to do is we want to cancel out the grams of NaClO2. In order to do that, we need to use moles of NaClO2. So what we have to do is use the molar mass here. And so we're going to add up 23 for sodium. We're going to add up the molar mass of chlorine, and then 2 oxygens is 32. So the molar mass should have been 90.45. Okay. So we're going to write 90.45 per 1 mole of NaClO2, and then the grams cancel out. Okay, next I'm going to take moles of NaClO2. And since I'm looking for ClO2, I'm going to plug in moles of ClO2. We look at the mole ratio. It looks like it's 2 to 2. So it's going to be 2 and 2. And so what we're going to do is we're going to cancel out moles of NaClO2. But luckily for us, there's a 2 on top, 2 on bottom. So the 2's cancel out. And then last but not least, we take the moles of ClO2, the molar mass of ClO2, excuse me. And so all we need to do is add up chlorine, which is 35.45, plus 32 from both oxygens. The molar mass of ClO2 is 67.45, and then the moles cancel out. Okay, so if we plug and chug into the calculator, we got 15 divided by 90.45. We're going to multiply that by 67.45. That'll give you 11.185 grams of ClO2. So 11.18, I'll do 6 grams of ClO2. Okay, so I know it's been a while since we did regular stoichiometry, but this is basically telling us if we have 15 grams of NaClO2, it can produce 11.186 grams of ClO2. Okay? Yeah, so if you guys messed up anywhere, it's all good. First and third fractions are molar mass. If you guys calculated that wrong, that's okay. And then this is from the balance equation. Okay, so I'll pause right there. Any questions on how we got this value? Okay, now we'll do the other one. So we did NaClO2. Let's figure out how many grams of ClO2 that chlorine gas can make. Now, for chlorine gas, only thing it tells us is that we have 2 liters of chlorine gas. Okay, but it also gives us the pressure and the temperature. And so what we can do is we can use our new gas law skills, and we can use PV equals nRT, and we can find the moles of chlorine gas in there. So if I rearrange this equation, I can get N is PV divided by RT. Okay, and if I can find the moles of chlorine gas, very easy to do some stoichiometry to turn that into grams. So let's just plug in the values that we have. We have 1.5 atm for the pressure. That's from right here. We have the volume, which is 2 liters. We got that right here. Then divided by the R value, the gas constant, which is 0.821. And then the temperature is 21 degrees Celsius, but we need to add 273. So that's going to give us 294 Kelvin. And so from there, what that lets us do is calculate the moles of Cl2. And so I'm going to go to my calculator. I'm just going to multiply the tops, 1.2 times 2, which is 3, divided by 0.0821, and then divided by 294. That'll give me 0.124. So 0.124 moles of Cl2. Any questions about how we got that? Okay, it's just basic ideal gas law. Okay, now we're in a place where we're more comfortable. We got moles of Cl2, so we can set up a fraction. I want to get rid of moles of Cl2, and I want to find moles of ClO2. So we just go to the balance equation. We have nothing in front of Cl2, so we have 1. We have a 2 in front of ClO2, so we put a 2. These guys cancel out. And then last but not least, we can use the molar mass of ClO2. We got that earlier, 67.45 grams of ClO2, and moles cancel out. And bada bing, bada boom, we have the way to find the grams. So we're going to do 0.124 times 2 times 67.45, and there we go. We get 16. I'll get rid of the calculator. 16.728. Okay, so these are the two values that we get. And then since we have to talk about limiting reagents, if you notice, which one of these compounds limits the reaction? Yeah, NaClO2, since we run out of that. So this is our limiting reagent. We don't make 16. Instead, in reality, we're going to make 11.186. So again, a lot of the AP Chem problems, they're not really like super complex stuff in the sense that the skills aren't too bad. It's just a lot of things that you've learned already. It's just kind of mixing it together in a really annoying way in order to get a problem. Because you guys know stoichiometry, you know limiting reagents, you know ideal gas laws. They're easy when you do it separately, but trying to figure out how to use them all together is the challenging part. And that's kind of the trick of the test. Yeah, and the wording, it does kill you. But maybe it's because I'm writing some of these problems and my English is not that good. All right, so we're gonna take a 5-minute break while you guys finish copying that down. And then after that, we'll do 5.20, which is the last problem that's gonna be on this workbook. And then again, next 2 class sessions, we're gonna do a bunch of practice problems. And so when we come back from our break, we'll go over the last problem together. Yeah, there's a clipboard. To sign up before you go to the restroom. Alrighty, guys, let's move on to the last problem. So I'm gonna erase this, and then we'll finish this one up, and then we'll get started, or we'll be done for the day. Okay, now this problem, I'm just gonna let you guys know straight up, is a pain in the butt. Okay, a lot of conceptual thinking, and you got to be a little creative with this problem. Okay, so I want you guys to just take a minute to read it real quick before you start any of it. Just read the problem. See if you guys can jot down any of the information on your paper, and that way you can start setting it up. But take a minute just to read it and just kind of figure out what's going on. Write down some information you might want to extract from the problem, and then we're gonna go over it, okay? Yes. Alrighty, guys. So if you're still jotting stuff down, feel free, but I'm going to start going over this problem just so that we know what's going on. Okay, so in this problem, basically what is happening is you have a container, right? And inside of this container, you have a mixture of lithium carbonate and magnesium carbonate. Okay, so in here I have lithium carbonate, and hopefully by now you guys know these formulas, and or you're able to figure it out. And then we have magnesium carbonate. Okay, and then what happens is it's treated with excess hydrochloric acid. So we're going to add some HCl in there. Okay, now it tells you that it's a 10-gram sample. So that means in here we have 10 grams total. So the mass of lithium carbonate, so the mass of lithium carbonate plus the mass of magnesium carbonate is going to be equal to 10 grams. Okay, so the 10 grams is for the total mixture. So the mass of both of them combined is going to give you 10 grams total. Okay. Any questions about the setup so far? Okay. It says, so obviously these are going to react because hydrochloric acid is going to react with these ionic compounds. It's going to produce 6 liters of CO2 gas, and it tells you that it's at STP. So what that means is the volume of CO2 gas that's produced is going to be 6 liters. It's STP, which means the pressure is 1 atmosphere and the temperature is 273 Kelvin. Okay, so we've extracted all the information that is inside of this little blurb about this problem. Okay, now I'm going to start erasing some things just so we have space. Just make sure you copy it down or you have it, mentally noted. Any questions so far? All right, let's take a look at part A. Part A tells you, write the balanced equations for the reactions that occur between the acid and each component of the mixture. But you have to recognize that H2CO3 decomposes into liquid water and gaseous CO2. So if you guys notice, there are two different compounds in here, right? So I'm going to do part A. The first compound is lithium carbonate. The second compound is magnesium carbonate. And it's reacting with HCl. So we're going to add HCl to both. It's asking you to write the balanced chemical equations for both. Okay, so we learned how to do this in the previous unit with the double replacement equations. So I'm going to give you guys 2 minutes to try this out, to write both product sides of both reactions to balance it out. Just keep in mind that H2CO3 decomposes into liquid water and gaseous CO2. So try that out. I'll give you guys 2 minutes to try it. You can work with the person next to you, and that's going to be part A, just finishing up these two equations. Yeah.
When it tells us like the H2CO3 the water and the gaseous CO2, is that given or is that we have to figure it out?
So I've seen problems where it's not given, but you won't lose a lot of points if you just leave it H2CO3. So I would say if you have space to remember it, you can remember it, but it's not very vital. I say there's more important things to remember than that. Alrighty, guys, so I'm gonna start going over the balanced chemical equations. If you guys are still working on it, feel free to do so, but let's get into it. Okay, so let's look at the first one. We have lithium carbonate and HCl. Okay, so we're gonna double replacement. So lithium is gonna react with Cl. Okay, so what is lithium's MCI? MCI, what's the charge? +1, yeah. Remember that pattern on the periodic table? I know it's been a really long time since we looked at that. So if remember, if you look at the columns, it should be on the periodic table on the sheet protector at your table too. But lithium is +1. What about chlorine? What's chlorine's MCI? -1. So that means if we have one of each, they're going to balance out. So it'll produce LiCl. Okay, we're going to double replacement again. So we have carbonate and we have H. What is carbonate's charge? -2, yeah. If you take a look at the chart, it's on the sheet protector actually in front of you too with carbonate. Carbonate is -2. And then hydrogen's MCI we know is +1. So we're going to need 2 hydrogens to balance out the carbonate. Okay, but we can't stop right there because it tells you that it decomposes into liquid water and gaseous CO2. So we're going to just get rid of this guy right here. And we're going to write H2O plus CO2. And this makes sense because if we take a look at H2CO3, let's just kind of count the elements. We have 2 hydrogens, so there's 2 hydrogens. We have a carbon right here, we have a carbon right there, and we got 3 oxygens. So it balances out on its own. Okay? And so if we wanted to balance this equation, the only thing that we have to do is put a 2 in front of lithium chloride, and there you go. That's going to be your balanced chemical equation right there. Oh, you're right. Man, thank you. See, this is why I need y'all. Stroh's brain is not that good. All right. Now we have the other one to balance out. So we're going to do that double replacement action again. So we have magnesium chloride. So magnesium's MCI is +2. And then we're going to produce H2CO3 again, but that's going to decompose into H2O and CO2. Okay. And then for the balancing, you just need to put a 2 in front of HCl. And there you go. That should be good. Am I right this time? H2. Yes, I am right this time. Yes. Okay, so that's part A. Now for part B, it's asking you to calculate the total moles of CO2 that's produced from these reactions. Okay, and so what we're going to do is we're going to take the values that we have right here. I'm going to do part B up here. I'm going to do it in black ink. Okay, we want to find the moles of CO2. And so what we're going to do is we're going to do PV equals nRT. And we can just use this equation because the problem tells us the volume of CO2 directly, right? If it said like, oh, the total pressure volume or the barometric pressure, then it wouldn't be just CO2. But it tells you CO2 directly. And so we can just use this equation. We're looking for moles, so we're looking for N. So if we rearrange this equation, we'll get PV divided by RT. And from there, it's just a simple plug and chug. So I'll give you guys a minute to solve that out, and then that'll give us the moles of CO2. So I'll give you a minute to finish that up, and then we are done with Unit 5. Great work, everybody. It is great work, dude. This is a hard class. It's a difficult class. You guys are doing a great job. I'm a very anti-procrastinator person. Alrighty, guys, so let's finish this up and then we'll be all done. So we just need a plug and chug. So for our pressure, we have 1 atm. For our volume, we have 6 liters divided by the R value, the gas constant, which is 0.0821. And then the temperature is 273. I guess we can do 0.15. Not going to make a big difference. And then we just plug it into our calculator. So I don't have space now. So we're going to do 6 on the top. 1 times 6 is 6 divided by 0.0821 divided by 273.15. That should give you 0.26. Okay, so the moles of CO2 gas is 0.26, I guess 8 moles of CO2. All right, and then from there, if the question asks you further, you can calculate the grams, right? You can also use this to figure out how much total, what the percentage is, because it makes CO2 from both sides. You would just have to find the difference based on the mole ratio, but we're not going to do that. Okay. Alrighty, guys. Well, congratulations. That is unit 5. So the next time we come and see each other on Tuesday and Thursday, before the test, we're gonna do a bunch of practice problems. I know we haven't had a day where we just sat down and did problems, even though that's kind of the most important thing. We'll do that for the next 2 class sessions, and then after that, when I see you guys next to Monday, we're gonna be taking the exam.
The practice problems include